For problem 1, we have the situation where we have the ball. Once it leaves the hand, it reaches the highest point, and then at the highest point we know that the velocity is 0. We know that the velocity when it leaves the hand is 20 meters per second, and we want to find this maximum height. Let's call that y2. This is y1 equals 0. And because once the ball leaves the hand, mechanical energy is conserved, since we don't take into account air resistance, then we can say that mechanical energy E is equal to the kinetic energy plus the potential energy, and E at point 1, which is when it leaves the hand, has to equal E2, which is at the highest point. So this is the kinetic energy at 1 plus the potential energy at 1, and this has to equal kinetic energy at 2 plus the potential energy at 2. At 1, it's 0 height, so it doesn't have any potential energy, and at the highest height, the velocity is 0, so that's cancelled. So in this case, K1 has to equal U2. The kinetic energy is 1/2 mv1 squared. The potential energy is given by mg times the height, which in this case is y2. So y2, if we solve from the equation, we get that y2 equals v squared over 2g. And these values we know, so we have 20 meters per second quantity squared divided by 2 times 9.80 meters per second squared, and that gives us a maximum height of 20.4 meters. In part B now, we're told there's a force that the hand exerts on the ball, and that's the reason why the ball is tossed upward and it moves upward, and we want to find what that force is, assuming it's constant. So we need to find the work done by this other force, and we can say that we know just before leaving our hand, let's call that K1, which is kinetic energy of ball just before leaving hand. That will equal 0. The potential energy at 1, which is the potential energy just before a hand moves, is going to be mgy1, and then kinetic energy 2 is the kinetic energy of ball just after it leaves our hand, and that's going to equal 1/2 mv squared, and then the potential energy is again mgy2. And if we look at the picture, at a picture that we can think of this as ball just before leaving the hand, This is the ball just after. There's some exaggeration here. This is the ball we're going to need this for part C at y3 equals 15 meters. So this is just that y2 equals 0, and this is where y1 equals negative 50 centimeters. So it's the ball is still in our hand for about half a meter while we're moving upward. So what we can say is that from conservation of energy, K1 plus U1 plus the work done by this other force has to equal K2 plus U2. And notice there's a difference now between this mechanical energy and the one we used in part A, because there's an external force here that we're taking into account, which is the one from our hand. So the work done by this other force, other than the kinetic energy or the potential energy, is going to equal K2 minus K1, right? If we combine some of these terms, U2 minus U1. And if we plug in these values, we have 1/2 mv 2 squared minus K1, if you remember, was 0, plus U2 is 0, it's just after it leaves the hand, minus mg y1. So this equals 1/2 times the mass, which is 0.145 kilograms, times the velocity, which is 20 meters per second quantity squared, minus the mass, which is 1.45 kilograms, times g, which is 9.8 meters per second squared, times the height, which is the height that the ball went through before it leaves our hand. And if we do this, we find that this is about 29.7 joules. And if you remember the equation for the work is the force times the distance, which implies that the force, it has to be the work divided by the distance. So this is 29.7 joules over the distance that the ball travels in our hand is 0.5 meters, which gives us about 59.4 joules. And since we're looking for significant figures, we can say this is just newtons, not joules, sorry. For part C, we have still a mechanical energy conservation equation. Since there's no forces on the ball anymore, we can say that mechanical energy is conserved without any external forces. And now we can say that, let's call this E2 and E3 based on our picture. So we have kinetic energy 2 plus U2 equals kinetic energy 3 plus U3. And we know that the gravitational force is 0 at 2, and we found what the K2 is previously. So we can say that kinetic energy 3 is the same as K2 minus U3, which is 1/2 mv2 squared minus mgy3. And if we plug in the values, we get 1/2 0.145 kilograms times V2, if you remember, was 20 meters per second, minus m, which is 0.145 kilograms. G, again, is 9.8 meters per second squared. And Y3, excuse me, is now 15 meters, because that's where we want to find the speed. So if we do this, we get that the kinetic energy at point 3 is 7.7 joules. So that means that 1/2 mv3 squared equals K3, which means that V3 equals square root of 2K3 over m, which is 2 times 7.7 joules over the mass, which is 0.145 kilograms. And because we're taking the square root, it could be that we have a positive or a negative velocity. Positive meaning the ball is going up. Negative means the ball is coming down at that point, which is possible because it's not above the maximum height. And if we do this and we take into account significant figures, we get about 10 meters per second plus or minus.